All right, so to get started in Chapter 2, Section 2, we're going to be introducing the idea of a limit. So for a second, we're going to be very imprecise. We will make the definition of a limit very precise a little bit later. But for right now, the idea of a limit is we want to get close to the value x equals 2, but not actually to the value x equals 2. And so at first you might think, well, what is this going to accomplish? And trust me, it's important, as we'll see. But for right now, the idea of a limit in a certain sense is we want to know what the outputs of the function are doing when the inputs x get close to some value, but not actually equal to that value. In fact, limits don't care what the function value is at that actual point. So in this case, we want to get close or near to the value x equals 2. We don't actually care about what the value at 2 is. We just want to know what happens as x gets closer and closer and closer. So in terms of this idea, if we imagine a number line, we want to get close to the number 2. Well, there are two directions from which we can approach the number 2, right? So I could get closer to the number 2 from the left side by picking numbers that are always less than 2 and closer to 2, or I could approach them from the other side by picking numbers that are always greater than 2 and decreasing down to that value. So if we look at this first table of values for x, which I'm going to highlight in red because they correspond to the values of x that are less than 2, if we notice, we have the value 1. Well, the number 1 is not very close to 2, so we could get a little closer, like 1.5, right? And then we could get closer, 1.9, and then we could get even closer, 1.99 and 1.999, and we could do that ad infinitum forever, right? And never get to the number 2. We could just keep adding more 9s, like 1.999999999 on forever. And we might notice that this value seems to be getting close to something as we do that. So something we may or may not remember about our calculator is that we can actually just put functions in. So if we go y equals, we can type the function in, y equals x cubed, take away 1. And most of us are familiar with the table where we can do some stuff like this, and it generates a table that looks like this. But we also have another option that we can do with the table, which helps us evaluate a whole bunch of points very quickly. So to change our view, we need to go to our table set. So table set is the secondary function on the window key right here on our graphing device. So we go second and window. And for our independent variable, we're going to change it from auto to ask. So normally when it's on auto, that's how it just generated that table where you can scroll up and down with your arrow keys. If you change it to ask on the independent variable, and then let's go back into our table, you'll notice it doesn't create anything. In fact, they're blank. What it's asking us to do, when it says ask, we have to tell it what x values we want to use. So if we look at our table here, well, we want to know what the x value is at 1. So we put in 1 and we press enter, and it tells us. And if we want to know what it is at 1.5, we press enter, and it tells us. And then 1.9, and then 1.99, and 1.999, and 1.9999, 4 nines. And we notice each time we add another 9, I'm going to do one more even though it's more than what's on the sheet. In fact, I'm going to put 6 9s on this time. And finally, my calculator actually just rounded 6 9s to 2. So let's get rid of that. We get these values. So it appears as we get closer and closer to x equals 2, what does our output appear to be getting closer to? Well, we had 6.88, 6.988, 6.9988. If you had to guess what is the output getting closer to, what would you say? I'd go with 7, right? And the more 9s that we added, the closer that this is getting to those values. Okay, so let's go ahead and clear all these out by pressing our delete key and rinse and repeat, but this time we're going to use the values on the other side. So we're going to try 3, 2.5, oops, let's try that again, 3, 2.5, 2.1, 2.01, 2.0001, and 2.0001. And this time we see pretty much the same thing happening, but now we are approaching this time with x values that are larger than 2. So here. And once again, we notice that our output seems to be getting closer and closer to the number 7. So no matter which direction I am approaching the value x equals 2 from, the output, or the y value, seems to be approaching the number 7. All right, so this is the gist, or a very simple idea of what it means to be a limit. We're going to make this more precise as we move forward, and we'll give some formal definitions. But now, let's kind of summarize in our minds for a second. So I want everybody to take 30 seconds and think to themselves, so what is a limit? All right, so first thing with notation for limits, we're going to talk about them as this. So first of all, let's start with our symbol. Yeah, let's not use a highlighter. So our symbol for a limit is going to look something like this. We write the word limit, or lim, L-I-M, and we say x, we use a little arrow, and I'm going to use an A for right now. So the limit, so lim, x, a little arrow pointing to A, of f of x is equal to L. The symbol is red, as, so this part is the limit as x approaches A of f of x equals L. So our symbol is an abbreviation of that entire sentence. The limit as x approaches A of f of x equals L. So we're going to write that for a lot of things. And we will use this arrow a lot. So if we see something like x arrow 3, this tells us that x approaches 3. as we saw in the previous example, when we were talking about x approaching 2 or getting near the value of 2, there were two directions by which we could approach the input value x equals 2, right? We can come in from the right and we can come in from the left. So we have some notation for this as well. So the symbol x approaches 2, and if I put a little minus sign where an exponent would normally go, this tells us the following, which is the limit, or not the limit, there's no lim in this one. So this is x approaches 2 from the left. And that is what this part means. And if we do the same thing, we have an x, an arrow, a 2, but if we replace the arrow with a plus sign, this tells us it's going to come from the right. So when we are writing down these limits, if you see a plus sign where an exponent would go, it means we're approaching that value from the right side. If we see a negative sign where an exponent would go, it means we're approaching it from the left side. So up here in example 1, when we were approaching the values of x equals 2, using values like 1, 1.5, 1.9, 1.99, we are using values of x that are smaller than 2, so we are getting closer to the value of 2 from the left-hand side. Similarly, when you look at the blue part of the graph, we used 3, 2.5, 2.1, we were using values of x that were bigger than 2. So we are then approaching the value x equals 2, but this time we are doing it from the right. So those are our possibilities for our notations for limits. All right. Now we have our definition out of the way. Let's take a look at example number 2. Actually, before we do example number 2, we need one more definition, and they're actually out of order on your handout. So we need the definition of a two-sided limit. So the definition of a two-sided limit is the following. So if the limit as x approaches a from the left of f of x equals L, and the limit as x approaches a from the right of f of x is also equal to L, then we say the limit, and when we say limit without any quantification, like not from the left, not from the right, that means the two-sided limit exists and is equal to L. In symbols, what that means is if the left-hand limit exists and is equal to the right-hand limit, which also exists, then the two-sided limit, the one without a positive or a negative, exists and is equal to the same value. So basically what this definition is telling us is that the two-sided limit exists if both the left-hand limit and the right-hand limit exist, and they are equal to the same thing. That common value that they have is the two-sided limit. So if we go back to our example number 1, what was our limit as x came in from the left here? So our limit as x approached 2 from the left of x cubed minus 1 was equal to 7. And what was our limit as x approached 2 from the right of x cubed minus 1? It was also equal to 7. So the left limit was the same as the right limit. So then together, what does that tell us? That the two-sided limit existed and is equal to the same thing. So that's what our definition says. And right now you're probably thinking, well, how would it be possible for a limit from the left to be different from a limit from the right? Well, let's look at some examples and see what happens. So in calculus, we're going to think about functions in a very different way than we probably have in algebra. We're going to deal with functions that behave very differently. All right, so now, after all of that, we are ready for example number 2. So example number 2 says, use the graph below to answer the following questions. Let's take a look at our following questions. So I will start with the I do column, and then we've got the second column is for you guys to practice. All right, so the first one we're asked is find the limit as x approaches 1 from the left of f of x. And f of x is given in this graph. So the value that we're concerned with is the value x equals to 1, which is right here. And if I'm going to approach from the left, the points to the left of 1 are going to be here, and then the points to the right of 1 are going to be over here. So since I'm approaching from the left, that means I'm going to be moving along my graph, and remember, x is approaching 1 from the left. The limit is what value is y approaching. But before we start this, when you have an open circle on a graph, what does that mean? Included or not included? Not included, right? And if it's included, what do we use? A filled in dot. Okay, so as I get close to the value to 1 from the left, what is my y value? Well, what's the y value here? Is close to -7, right? So the limit, imagine you're riding along the graph, so you're moving along this curve right here. As the x value gets close to 1 from the left, what is our output or our y value getting close to? So as we slide down that graph, we get close to that open circle. Even though that open circle is not part of the graph, our value is close to -7. So we would say that our limit for this is going to be -7. Okay, so now we're asked to find the limit as x approaches, this time with the plus sign. We know we're going to come in from the right. And as I get close to 1 from the right, this time I'm coming down my graph here. So close to 1. What is my y value getting close to? Well, this time it's getting close to -3. So then my limit as I approach 1 from the right is going to be -3. So then for part C, what is my two-sided limit going to be? Well, does my left limit equal my right limit? No. So then we say it does not exist. So in WebAssign, they're going to have you just put DNE for does not exist. They'll put that in the instructions to the problem, so don't worry, you don't have to remember DNE. But DNE is the abbreviation for does not exist. So remember, when does the two-sided limit exist again? When the left limit is the same as the right limit. So in this instance, our left limit was -7, our right limit was -3, so the two values were not equal, so the two-sided limit doesn't exist. Lastly, it now asks us to find f of 1. Well, if I input 1, I have my filled-in dot right here, and that has ordered pair 1, 5. So then f of 1 would be equal to 5, right? So this graph of this function does not have a limit at x equals 1. It has a left-handed limit, and it has a right-handed limit, and the function even exists there and is equal to some other number, say 5 in this case. All right. So now it's your guys' turn. I want you to go ahead and look at your U-tries. So it's going to have you do a similar analysis. All right, so the point that we're interested in getting close to is x equals 4, which is right here. So if I start coming into the graph, on the graph, if I come in from the left, I'm going to be riding that curve up until I get to this point. So my y value appears to be getting close to 6. And if I come in from the right, that's going to be using points over here. So then if I ride my graph into that point, I'm getting close to here, and my output value is going to be -2. So once again, are the two values equal? No, 6 does not equal -2. So our limit as x approaches 4 of f of x is once again going to be does not exist. Moreover, now I get to f of 4, and I kind of wrote over it, but there was a filled-in dot there, right? So f of 4 is going to be equal to 6. So in this example, f of 4 was the same as the limit from the left, but f of 4 was different from the limit from the right. All right. next example says graph the function f of x and use the function to find any points where the two-sided limit does not exist. Well, let's So to help us make a little more sense about this problem, let's look back at the two things we just did in the previous problems. So we want to find the points on the graph where the two-sided limit does not exist. Well, in the part that I did and the part that you did, we both had that the two-sided limit did not exist. And what happened at those x values to the y values? Well, if we look at a picture of our graph at x equals to 1, we'll notice the graph breaks into two different pieces. So we'll notice it moves vertically right here, and we're going to refer to this as a jump. We'll notice once again we had a jump right here. Wherever our graph breaks and jumps like this, we're going to have that the two-sided limit doesn't exist. Because if the graph jumps, the limit from the left can never be the same as the limit from the right. Because as I come in from the left, I get one value, and when I come in from the right, I get a different value because there was a jump that separated those 2 points. So we're going to refer to this as a jump discontinuity in the graph. So those are going to be the key areas that we are going to look for in order to determine where the two-sided limit does not exist graphically. All right, so let's go ahead and actually graph this thing. So the first thing we have is negative 2x if x is less than negative 3. So I'm going to highlight that domain, so that's right here. And then I'm going to have the domain. I'm not going to do the single points as a domain. I have my next domain is negative 3 is less than x is less than 0. So that's going to be right here. Then my next domain is going to be from 0 to 5. Well, that's right here. And then my last domain is bigger than 5, and that's going to be right here. So when graphing a piecewise function, remember we just graph each of the pieces on their respective domains. So in my orange domain, I'm graphing negative 2x. Well, what does the graph of negative 2x look like? It's a line with slope negative 2, right? So this one is a line with slope negative 2. And if I put in any point in the domain, I can get 1 point and then use the slope to do that graph. Well, notice negative 3 isn't in the domain, but we can still plug it in. So that gives us negative 2 times 3. So negative 2 times negative 3 gives us positive 6. So that's going to be the ordered pair negative 3, 6. But this is not included, because I have a strictly less than, right? So that means at negative 3, I go to 6, but I don't put a filled in dot. What would I put on my graph? An open circle, right? So here I'm going to get an open circle, and I know the slope of my line is negative 2, so I go left 1 and up 2 to get another point, and that gives me my linear chunk there for that line segment. So now I've graphed the orange bit. This next part says negative 6 if x is equal to negative 3. Well, then that's really just the ordered pair negative 3, negative 6. So I go to -3, -6, and I fill in that point. So now I'm to my blue stuff, and it says -x plus 3 squared plus 6 if -3 is less than x is less than 0. Well, this is the graph of a parabola, and it's in vertex form, right? So where is my vertex going to be? Well, the plus 3 shifts it to the left 3 units, and the plus 6 shifts it up 6 units. So this is a parabola with vertex -3, 6. And we'll note that my a value equals -1. So I go to -3 and 6. Oh, that's right here. It's at that same point. Once again, it's not included. Since my a value is -1, that means my parabola opens down. So I go over 1, down 1. I go over 1, and then the next square, 1 squared is 1, so we went down 1. We go over 1, 2 squared is 4, so we go down 4, 1. We go over 2, down 4, so 2, 4, and so forth, and we put our last one in. If we put in 0, we're going to get down to -3. And at at 0, sorry, I put a filled in dot, but we're not equal to, so we get and if you don't want to figure those out by hand, we can do that on our calculator, right? So you just turn on your calculator. Remember, we have our table in ask mode, so we have to go second table set, change it back from ask to auto, and we go y equals, and you can just put that in -x plus 3 squared plus 6, and if we go second table now, we can check our values, right? So -3, 6, because we knew it was a parabola. Okay. -2, positive 5, and then we had -1 and 2, and then 0, -3. So that gave us the points on our parabola. Now, once again, we're in the green here, and we're going to use x plus 1. Once again, this is a line with slope 1, y-intercept 1. So we go here, and we have slope 1, and we're going to do this all the way till we get to 5. So up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1, up 1 over 1. We'll connect the dots for our line. And then finally, for x greater than or equal to 5, we have -2. So we go to -2, we fill it in, and we draw a piece that looks like this. So that is our piecewise function. So based on our definition, where does our graph jump? So the graph jumps at x is equal to 0 and x is equal to 5. So the two-sided limit does not exist at x equals 0 or x equals to 5. So at the point x equals -3, our graph didn't jump. We have an open hole at that point right here. So, in fact, the value of it's defined all the way down here. So this is what's called a point discontinuity. because it doesn't jump, but the graph is not continuous there because it has a hole. So then the question then becomes, at a jump discontinuity, we know the two-sided limit doesn't exist. At a point discontinuity, or a hole, would the two-sided limit exist? Sure. Because as I get close to -3 from the left, what's my y value? 6. And as I get close to -3 from the right, what does my y value get close to? 6. So removing one point from a graph or having a hole does not affect the two-sided limit. So holes, we can have the two-sided limit will exist. At a jump, the two-sided limit will not exist. So these are the two types of discontinuities that a function can have. It can either jump or it can have a hole. So we've seen something like this in our pre-calculus class when we saw vertical asymptotes. At a vertical asymptote, the graph jumps from -infinity to +infinity. So that's called an infinite jump discontinuity, and it falls into that same thing. It's just you're jumping from -infinity to +infinity, and that's okay. So all right, so let's pull out our graphing device and draw a picture of this. So we go y equals, and we put in our e raised to the alpha y equals to get our fraction 1 divided by x. And then we go graph, and we get something that looks like this. So it appears as we get close to x equals 0 from the left, our graph goes up and up and up forever. It shoots off up to +infinity. And as we get close to 0 from the right, our graph seems to be getting close here. So then the limit as x approaches 0 from the left of e to the -1 over x looks like it goes up to +infinity. And the limit as x approaches 0 from the right of e to the -1 over x looks like it gets close to 0. So if the left limit goes to infinity and the right limit goes to 0, are those two things the same? No. So does the two-sided limit exist? No. So the answer to this is does not exist. The two-sided limit does not exist. Because what happens with our graph here? Oh, we had a jump, right? Because was it connected? No. So the only way the two-sided limit can exist is if the graph is connected at the point in question. But here, it goes to infinity on one side and goes to 0 on the other. It's definitely not connected. So we have a jump, and the two-sided limit does not exist. All right. So let's talk a little bit about infinite limits and vertical asymptotes. If the limit as x approaches a from the left of f of x is equal to ± infinity, or the limit as x approaches a from the right of f of x is equal to plus or minus infinity, then the line x equals a is a vertical asymptote of f of x. So coming back to our graph here, since our left limit equals positive infinity, we're going to have a vertical asymptote at x equals 0. And we'll notice our graph, as it gets closer and closer to it from the left, it shoots off to positive infinity. This is different than the vertical asymptotes we saw in pre-calculus, where it always went to positive or negative infinity on both sides. That's only true for a certain class of rational functions. As we'll discover, we can have functions like this where it goes to infinity on one side and goes to some value from the other side. But for rational functions, the limits will exist in the way that you remember from Math 187. And we'll do some examples of that actually very shortly. So the next thing we need is a fact or a set of facts that needs to be memorized. So limits for when we have rational functions. So we know you can't divide by 0, but we also know that when we're taking limits, we're just getting close to those values. We're not actually getting to those numbers, right? So, for example, looking back at our u-try, we're getting close to the number x equals 0, but we can't actually put 0 in, because if we look at our exponent, what's 1 over x? If you put in 0, what's 1 divided by 0? Well, it's undefined, right? Doesn't exist. But we were able to find limits from the left and the right for each of these. So we're going to take this a little bit further. So the idea is, while taking a limit of a rational function, if the numerator gets close to a constant and the denominator gets close to 0, so a constant divided by 0 will always give you positive or negative infinity. The sign is determined by the signs of the numerator and denominator. So if the constant was -5 and the denominator was getting close to 0 from the right, well, if we're coming into 0 from the right, are the numbers positive or negative? Positive. So if I had a negative divided by a positive, what's the outcome? Negative, so we would get negative infinity. So we're going to have to do some sign analysis as we're calculating these limits. So a constant divided by 0 will always give you positive or negative infinity, where we have to calculate the sign. If you have a constant divided by plus or minus infinity, you will always get 0. Because if you think about it, if the denominator is getting really, really big, 1 divided by 1,000,000 is 0.000001. That's a pretty small number. Then you get bigger and bigger, a billion, a trillion. You just keep putting more zeros on and it gets smaller and smaller. It will always approach 0. So constant over 0 is infinity. A constant over infinity is always 0. So those are going to be our rules that we're going to use to help us calculate these values. So I know that that's not super clear yet, so let's take a look at example 4 and see if we can clear up exactly what we're talking about. So example 4 wants us to find the two-sided limit as x goes to 3 of f of x. So we're going to be getting close to the number 3 from both the left and the right. So if we're coming in from the left, that's over here, we're going to be using x values that are less than 3. And when we come in from the right, we're going to be using x values that are bigger than 3. So now let's take our limit from the left. So when I do my limit here, the top, the numerator is a constant. And our denominator is going to be, okay, so I'm approaching from the left, so I'm using numbers that are smaller than 3. So something smaller than 3, take away 3, is that going to be positive or negative? So what's 2.9 take away 3, positive or negative? Negative. So that means our denominator is going to be negative. And so let's think 2.9 minus 3 is negative. So a constant divided by a negative as we go to 0 is going to be what? Well, constant divided by a negative, if we have it going to 0, constant divided by a negative gives us plus or minus infinity, and our constant is positive, because 1 is a positive number. So a positive divided by a negative gives us what? Negative. So we get negative infinity. So let's rinse and repeat as we come in from the right. So if we take the limit as x approaches 3 from the right of 1 over x minus 3, we're going to be doing the same thing. The numerator is exactly the same. It's still the constant 1, which is positive. But now we're approaching x using values bigger than 3. So if I have something bigger than 3 take away 3, so like 3.1 take away 3, all right, that's not an equal, that's a subtract. Is that going to be a positive or a negative? Positive. So it's positive and it's 0. So then a constant divided by 0 is infinity again, but this time we have a positive divided by a positive, which is positive. So our limit from the right would be positive infinity. If we draw a graph with our graphing calculator of this function, so we go 1, alpha y equals x take away 3, and we go graph, we get a picture that looks like this. And indeed, as we get close to 3 from the left, what happens to our graph? It shoots down to negative infinity. And as we get close to 3 from the right, what happens with our graph? It shoots up to positive infinity. So remember, in pre-calculus, we just had to pick x values to figure out if it was going up or down. So now using the idea of limits, it tells us what that behavior around the asymptotes is going to be. So in this case, our left limit was negative infinity, and our right limit was positive infinity. All right. Once again, it's your turn. All right, so let's start with our analysis. So if we take the limit as x approaches 3 from the left of 1 over x minus 3 squared, so we can make a nice observation in this problem that simplifies things. If you square something, what is its sign always? Positive, right? Because a positive times a positive is positive, and a negative times a negative is also positive. So what's our denominator always going to be? Positive. And as x approaches 3, we're going to get 0. So this is going to be positive 0 over a positive 1, so constant. That's positive. So a positive constant divided by positive 0 is positive infinity. And we're going to get the mirror image coming in from the other side here. So 1 over x minus 3 squared, and it's still going to be positive because something squared is always positive, and the numerator didn't change, so it's a constant, and it's positive, so we also get positive infinity. So the limit from the left is the same as the limit from the right, which is both positive infinity. So the two-sided limit is positive infinity because the left limit equals the right limit. So we get, in this case, they're the same, and we get the value positive infinity. All right. So now we're going to take a look at our last example from this section. It says, find the vertical asymptotes and the wholes of f of x equals x minus 4 all over x squared minus 2x minus 8, where x does not equal 4, and it's equal to 6 when x equals 4. So if we were to just glance at the top part, how many vertical asymptotes would you expect this graph to have? Well, what's the degree of our denominator? 2. So if we factor a quadratic, how many solutions can we get? 2, right? So we would expect that we're going to be dividing by 0 in how many places? 2. So we would expect that there might be 2 vertical asymptotes. Let's draw a graph because we're going to be a little bit surprised. So we go y equals, get our fraction, so we go x plus 4 over x squared minus 2x take away 8. And if we graph just that, I have a typo there. Yes, I was like, that is not the right picture. So let's try that again with the right thing in. So I get something that looks like this. How many vertical asymptotes does my graph appear to have? It appears to have only 1. So let's do some investigation and see what happens. So as I mentioned, we can factor quadratics. So let's go ahead and factor this thing up a little bit and see what we get. So x minus 4 doesn't factor over, and our factors of -8 that give us -2 are x minus 4 times x plus 2. And that is our function when x does not equal to 4. And when our function does equal to 4, what do we get? Or it's 6 when x is equal to 4. So we'll notice we're drawing that first graph when x doesn't equal to 4. But we also notice that 4 is a 0 of the denominator. So we would be dividing by 0 there. But that factor is also present in the numerator. So since x cannot equal 4, we can reduce to one over x plus 2. So we'll notice something very interesting happens. So we've graphed this one. Let's also graph 1 over x plus 2. So when we draw the graph, you're like, wait a minute, nothing happened. They look exactly the same. Because in fact, these two things are equal everywhere except for at what value? X equals 4. And we can confirm that by analyzing our tables. So we see that both of them are still undefined at -2. And we look, their values are the same everywhere, except for the first one says it doesn't exist at x equals 4. But everywhere else, they have exactly the same values. It's interesting. So what would that tell you? If they're equal everywhere except for at one point, how would their limits have to be related? Well, does taking one point out of a graph change its limit? No, because it would give us a nice little hole. So if two functions are equal everywhere except for one point, then they must have the same limits. So in this case, they're going to have the same limiting value. So what would the limit be as x went to 4 of x minus 4 over x squared minus 2x minus 8? Well, it's got to be the same, so it's going to be 1/6, right? So this is an interesting fact that is very useful. If two functions are equal everywhere except for one point, then they must have the same limits. Okay, so now we know what this is going to be, so we could draw a graph of this function. So where is this guy going to have a vertical asymptote? Well, where do we divide by 0? It's going to be at x equals -2. So then if we take the limit as x approaches -2 from the left, we're going to have a positive divided by a -0. And a positive divided by a negative is going to give us a negative. So we get -infinity. And if we take the limit as x approaches -2 from the right, we're going to get a positive in the denominator. So a positive divided by a positive is a positive. So this is our vertical asymptote at the point x equals 4. The function has a hole. To find the hole on a graph, we evaluate the reduced function at the excluded value. So our excluded value for the hole was x equals 4, right? If we plug f of 4, or I'm going to call it g, into our function 1 over 4 plus 2, we get 1 over 6. So the hole is located at the point 4 1/6. And this is our hole. So if we go back to our graph, and if I go second calculate and I try to calculate a value, if I select y1 and I put x equals 4, notice it tells me that there is no corresponding y value because it's not in the domain. But if I move around a bit, we could see if we plugged it into y2, which is essentially what we did, the reduced function, it tells us where that hole is on the graph, or where the two-sided limit would exist. If a graph has a hole, or if a function has a hole at the point a comma b, we can remove the discontinuity by defining f of a equal to b. So essentially what we're saying is if we had this problem like we did where we look at our table, we could make the original function continuous at x equals 4 by defining the output to be what at that point? 1/6, which was the missing value, what the two-sided limit was equal to. So we can remove the discontinuity at that point by defining it to be equal to the two-sided limit at that point. Because those functions are equal everywhere at one point, but one point. So if we define that one value to be the two-sided limit, it makes the function continuous there. So we can remove discontinuous points if we have a hole or where there's not a jump discontinuity. This technique won't work if the graph jumps, right? Because the left limit doesn't equal the right limit. So those, in a certain sense, are worse discontinuities than point discontinuities or holes. Because if only one point is missing, we can fill in the one point and everyone's happy. If we have a jump, there's something more complicated happening. And we'll talk about how we're going to deal with that at a later date. And so those are sometimes called essential singularities as opposed to removable ones. So, all right, let's go ahead and